Okay, I think it's recording. Okay, so all you invisible people, welcome to Lesson 20, and today we're going to learn how to assess our regression-based prediction engines. We'll look at some goodness of fit metrics, interval estimates of parameters, and interval estimates of predictions. Now, in defense of myself, this was kind of slapped together this morning, so it won't be as refined and tidy as prior lessons, but it'll work. First, let's go to the Olympics, and we're going to shoot some targets because as computer programmers and engineers, we've been hired to come up with a first-person shooter game called Olympic 10-meter air pistol. And we're developing it as a training tool for Olympic 10-meter air pistol participants. Not that it's a big thing, and here's a nice Wikipedia if you want to go look at it. And in the recent Olympics, who were the winningest nations in 10-meter air pistol and air rifle?
China.
Pardon?
China.
Not bad. Yes, they were one of them. Who else?
Russia.
It's actually China, India, and Russia in that order. All three of them are at war with each other right now, so I think that's pretty cool. The Americans, I think we had one woman in one of the air pistol rifle competitions, came in like 28th or something, which is not usual for the U.S., but this last Olympics, we were not very good performers. And that's because those other three had access to our computer program and were able to train effectively. So the whole point of that lead-in is we're going to have some graphics that's going to make pictures of targets and holes in the targets. But I had to start it with the Olympics because otherwise I would be being inflammatory and we'd have the FBI and coming through the door right now to haul me off to Club Fed. You don't want to go there in the wintertime. It's cold. They don't have heat. You don't want to go in the summer. They don't have air conditioning. There's a brief 2-week period in the springtime when going to a federal penitentiary is okay. So we'll load in some packages, mostly random and NumPy, and then a plotting package. And we're going to make a function. What's the name of this function? For anyone who's looking up there, it is show my target. And there's a whole lot of lines in it, but nothing is particularly difficult. All it's doing is making concentric circles, and then it's going to add them and then generate the plot. And I think I'm going to modify it and do that so that it doesn't return the address of the object. And so first let's look at the concept of accuracy. This really does have a point, so don't get too confused. When we're doing our prediction model building, one thing we're concerned about is the whole point of doing it is how good is the prediction. That would be called, in a marksmanship context, accuracy. How close to where we're trying to get to are we? And there we go. Welcome, Jasmine. A wee bit late, but you made it. Outside of my earshot, someone clue her into what the QR code will be on the last test. Unfortunately, I heard that. Yeah, I should have picked another profanity other than that. But, okay, so let's suppose in our software development, we're going to use a bivariate normal distribution, which is an ordinary normal distribution that we're used to, but it works in 2 dimensions. So it has an x and y component. And the closer we are to the mean, the mu, that's what we're trying to hit. That would represent a certain level of accuracy. But with 10-meter air pistol, especially with the Chinese and Indians sitting there yelling at you, and you're the Russian, your hand gets shaky, and the stuff goes flying every which way in that, and we'll represent that by sigma, or our dispersion. To get an idea how good we are, this is how we at least in Russia, this is how we decide who gets to go to the Olympics and who gets to have their organs harvested without anesthesia. So they're going to let them have 10,000 shots and see how they do. So we'll go ahead and, oh, it worked. That's rare. And there we go. So we've obliterated the center of the target. That would be ideal in hand grenades, horseshoes, global thermonuclear warfare, and apparently 10-meter air pistol. So if we're to look at that blob, on the average, where is most of the red dots happening? You can say stuff like right smack in the middle, which in our case corresponds to X location 0, Y location 0, right in the middle where it's supposed to be. But that was 10,000 of those. While those are very accurate, they're not very precise. Any two shots, one after the other, there's no hope in heck that they're going to fall anywhere near the middle. We are comfortable knowing that they're not way out here, which when I used to do competition, that was my stunt. I would use the outer edge of the target nobody else bothered with, so I didn't have to change it as often. And if we were to measure distances from the center, there's what our histogram would look like with our 10,000 shots. So does this Russian competitor get organ harvested, or do we let him go to Tokyo? It's Russia. We harvest the organs. I mean, come on. It's not like we're going to run out of poor folks to work with. So now let's continue our quest in our game. Let's see what happens if we adjust the aiming point. So now we've set it to -2, and again it's in 2 dimensions, so it should center at square root 1.4 away from the center, and it's minus, so it should be low and to the left. And we'll do that, and we'll still do 10,000 shots. Sure enough, low and to the left. Okay, so it looks like our simulator's working good. Now we need to deal with this mess of red dots. Low and to the left. Actually, odd to me that the mean is coming out as 2.8, but we're not near the bullseye. The second thing, so now we've discussed the concept of accuracy and aiming point. Next thing is precision, which is if we do repeats, how close to the mean do we get? So you can think of that in, again, the Russian air pistoler who's trying to keep his body parts for himself, or hers for herself, depending on which you're competing in, is how steady we are when we trip the shot. We have a really steady hand. That value of sigma, which is the dispersion term, should be small. If it's Thursday night and we've been downtown and we've had a little bit too much vodka and we're all over the place, then that number gets big. So we do that, and he's had a little bit too much vodka, because not only is his aim off, although it's pretty steady. So this is one of those guys, the more vodka they have, the steadier their hand gets. And again, there's our histogram of distances. And now we take the rest of the bottle of vodka. So this fellow's been practicing a long time. And very, very tight group. So that's a measure of precision. Precision is related to our variance term, how much things change from time to time. Okay, so now the last part, we obviously want to get it focused in. So the next concept is bias, and we tend to measure bias, which is what the offset is from what it should be, using our friends, the residuals. So again, in the context of our target shooting, the residual is the distance from the target to the estimate. And let's examine everything all over again. So this is going to rerun all the simulations again, possibly in my lifetime. Did it actually run? No, it didn't, because it's a piece of junk. This is one's taking an awful long time, because if you look at the loop, it's taking 1 million attempts. So this person really wanted to keep their kidneys, but they didn't do so good. Bye-bye, kidney. You didn't need that anyway. You weren't using it, drinking all that vodka. So there's 1 million shots. Our accuracy is off because we're nowhere near the black dot. And our precision isn't all that good, although it could be a lot worse. I mean, at least it's making a pattern. We've obliterated that part of the target. Fortunately, the whole center part is still usable, so we don't have to go change it. And there's what our histogram looks like. Does that look like anything else you've ever seen before in the history of your life? Yep. Not abnormal, but normal. Yeah, it's 1 million samples from a random number generator pretty much should produce a normal looking distribution. I'm actually surprised we get this much roughness right here at the pointy part. Sorry for the technical pointy part and curvy part. So we know we should be at 0, 0. So we tell Ivan, this is your last chance. If you can't get it at 0, 0, you're going to lose that other kidney, and that you don't work very long with just 0 kidneys. And so he took his 10 shots and excellently got his 0, 0. He's pretty close to the center, and pretty steady shot. And if the goal is to put all the holes in the aiming black, Ivan's done a good thing. He gets to keep his body parts. And a histogram of 10 things isn't very useful in this context. We see that the mode of the 10 things is 3/10 of a unit, but the mean distance isn't even in the histogram. But he says, I can do better. If I do better, can I have my kidney back? And it's like, yeah, okay, sure, why not? You've already got a big old opening in the side of your body anyway. We can stick a kidney in there. And so Ivan changes his dispersion from what it was to something much smaller. His aiming point is good. And now when we do it, it pretty much clobbers the center. It's not only give you your kidney back, we're going to go take the one from the Indian competitor, because they're not using it. And so now Ivan has 3 kidneys. We'll skip this last one. This last example graphically shows what happens when the target moves, like stuff does in real life. You get everything all dialed in. You've got your regression-based prediction engine working, and all of a sudden the target moves. Turns out that the material that you're marketing on your Amazon website is no longer popular. For whatever reason, people didn't want maroon scrunchies anymore because they all grew short hair or something. Okay, so with that introduction, let's remember ourselves about our friend's linear regression. It was a predictive technique that uses prior observations, so that's what's meant by the word historical, not necessarily in a temporal sense, to predict an output variable. So nothing new there. Why do we do it? Officially to explore predictor and output variables. Unofficially because it's part of this class and you've got another month of this left before you never have to see my lovely face again as an instructor. Unless you're in civil engineering and you take water systems or graduate classes, then you're screwed. Which will be the other meaning of the QR code. That's it. I'm going to get a QR code for a screw. Because if I'm going to go down, I mean, we've got to make this big. So how does linear regression work? If you recall, to estimate a value y we would stipulate a model equation. The simplest one is shown up here. Y is equal to beta x plus alpha, where the beta and the alpha are called the parameters of the regression. When we do it with computational linear algebra, the alpha gets buggered into the beta part, and it just becomes x beta, where x is now a design matrix that's comprised of the observations and usually a column of ones. Our goal is to find significant values of the parameters alpha and beta that minimize the difference between whatever the observed value of the response is and whatever the model value, which in this case is called y sub e. And ideally, if we can find the best possible values of the parameters, then we are happy campers, because we declare that's the line of best fit, and we can use it to predict values of y given the value x, with a further hidden stipulation that they actually are linearly related, because if they're not, it doesn't matter how ideal the straight line is, it's going to be a phony model. So how do we estimate those coefficients? We use something called ordinary least squares, not to be confused with extraordinary least squares. And we use that calculus stuff that we've taken in other classes, because you take, 4 math classes as a minimum. And if you can do arithmetic, you realize if I take computation, if I take the linear algebra class, I can get a math minor. And that's, at the current point, that seems like that's cool. It probably doesn't matter much, but by all means, one extra class, anyone who's in engineering can get a math minor. Might as well take the extra class. It's going to find you at the end if you can't fit your classes in anyway. Math department is good. So how did we do that? And we used calculus, and we rewrote the error. The error was y observed minus the model, which is the equation. And then we found that we can square that, which is how it's usually done. And in doing that, if we took the partial derivatives of e squared with respect to alpha and respect to beta, set those equal to 0, and solve for what was unknown, which were the alpha and beta, we discovered that we could come up with parameters. And those parameters were the necessary and sufficient condition for a minimum for that function. Now for grins, we did it with primitive Python, and then again with linear algebra, and then again with external packages. And hopefully you concluded that I don't want to do it with primitive Python and my own linear solver code. But there you go. Your head was about to do that. You should bring those little airplane pillows. That's what everyone's sitting along the back wall for. It's taken me 3 months to figure that out. So you can sleep through my soothing voice. Yeah, we call this online Ambien for you invisibles. Okay, so continuing with the story. How do we assess how good or how poorly our fits are? Well, first we want to remember our friend, the probability density function for the normal distribution, and there's a pun up there. It says, remember when we discussed it? Probably not. That's the pun. One way is to look at it as a probability density function, and what that equation up there tells us is if lowercase x is pulled from a normal distribution that happens to have a population mean of mu, which is that funny looking U-shaped Greek letter of the alphabet, and a variance of sigma squared, this tells us the density. So if lowercase x happens to equal mu, what is the value of e to the minus x minus mu squared over whatever it's divided by? Well, if x is equal to mu, mu minus mu equals the mighty 0. E to the 0 is 1. So whatever the other things is, it's 1 over, the result is 1 over that square root of that deal. And any other value of x is smaller than that. So if x happens to equal mu, then that's the highest probability density we could get. If x is a long, long distance from mu, say mu happens to be 0 and x happens to be 10,000. That's pretty far apart. So 10,000 minus 0 is? 10,000 squared is a bunch. So e to the minus a bunch is, that's e to the minus infinity essentially, approaches our friend 0. So yeah, if x is a long way away, the density associated with that's really, really small, approaching 0. So the equation tells us the density of our sample x from a random variable generator cap x when the true parameters are mu and sigma. If the density is kind of large, I mean approaching 1, we would infer that the value is relatively common and or frequent or likely or whatever English word you want to use to convey that that's probably came from that distribution versus not common, infrequent, unlikely. So let's suppose our value is 3. We can ask ourselves, so the terminology here is slightly wrong, but we'll go with it because I don't want to try to figure out how to retype it. What's the probability it comes from a distribution with mu equals 3 and sigma equals to 1 versus did it come from a distribution with mu 7 and sigma 2? So first we'll load all that gobbledygook in. So if we get a 3 from our generating process, the approximate chance that it came from that with a mean of 3 and a variance of 1 is roughly 0.4. But that same number coming from a distribution with mean 7, variance 2 is 0.02, quite a bit smaller. And that's all that equation is conveying to us. So if we were to just make a judgment call, we'd say it's quite a bit more likely from the first distribution than it came from either of those two at all. The PDF equation you can think of shows us how likely the values are to appear in a distribution. Keep that in mind later on because we're going to look at something called maximum likelihood estimation coming up pretty close on the guitar. Let's assume we were to take a bunch of samples from our process generator CapEx that we know come from some normal distribution and they're all independent, identically distributed. If that's the case, the total probability by definition is the product of the probability of each individual value. So if we were to ask ourselves what's the chance of a 2 and a 6 coming from distribution with mean 4, variance 1, or excuse me, standard deviation 1, it would be the value associated with the 2, whatever that its probability is, multiplied by the value associated with the 6, whatever its probability is. Put those together, and you can see in this case it gets small fast. We're going to leverage that shortly. So one method that's used to specify distribution of unknown parameters and then try to find what those parameters are is called maximum likelihood estimation. So think of what the words are saying. It's saying let's come up with some function that represents the likelihood of what I'm about to look at and then make it as big as possible by adjusting parameters, so our betas and alphas, if you will. So our linear model, whether we did it explicitly or implicitly, we've kind of implied that the errors are normal with a mean of 0 and a variance of sigma squared. And those are associated with the errors. We had another word for those errors. Begin with the letter R. Good. Yes, so if we were to make a histogram of the residuals, and that histogram looked like that, that would be a good indication that, yes, it probably is normally distributed. We also would be obligated to actually plot that histogram over the range of observations to be sure that it pretty much is keeping a same thickness band everywhere. Otherwise, it's called heteroscedastic, which is just a fun word to say. It means that the variance is changing with scale. And what I'm about to say, while you could use it for that, you would start to be getting into the world of wrongness. Okay, so let's pretend for the time being that that's indeed the case, that the errors or the residuals are roughly normally distributed with a mean of 0, meaning that we're aiming the pistol in the right place, and a standard deviation of sigma, and our shakiness is whatever sigma is. We can think of this epsilon as a noise parameter. The noise is fundamentally why the points don't actually fall on the line, assuming the process is linear. The error for each point is the distance from the point to our line. We'd like to explicitly include those errors in our model. One method of doing this is to assume the errors are distributed from a Gaussian distribution. Gaussian is just another name for normal distribution, with a mean of 0 and some unknown variance sigma squared. Gaussian seems like a good choice because in our case the errors look symmetric about where the line would be, and small errors are more likely than large errors, so it kind of fits the observational aspects of a normal distribution. So now our model, our data model, actually has 3 parameters. It has the slope and the intercept of the predictor line, which is what we're after, and the variance of the noise distribution. So we don't know the variance of the noise distribution until we specify a slope and an intercept, and then can start making those distance measurements. But keeping that in mind, our main goal is to find the best parameters for the slope and intercept of our line. So let's rewrite the model as a single conditional distribution given x. So if we were to do that, we would say that y is related to a normal distribution of theta 1x or beta x plus theta 0 or plus alpha sigma squared. So this is the equivalent to pushing the x through the equation of the line and then adding noise from the zero mean Gaussian distribution. Now we can write the conditional distribution of y in terms of the probability distribution. So this is just the equation of a normal distribution's probability density function, which we've seen already, but with new letters of the alphabet thrown in for job security in my case. We would write the function of whatever our observed response y is of x parameterized by theta 0, theta 1, and sigma squared. So that's kind of a weird notation, but that's actually very common in this context. The function is y equals some function of x. But that function of x has these additional parameters that may or may not be specified ahead of time. So you just put them into the argument list. It's a way of keeping notes to yourself. That these have to be provided for this whole thing to be evaluated. Is 1 over square root 2 pi sigma squared e to the minus. And then here we have the whole x part. Remember, mu is supposed to be 0, so we don't have to write that, over 2 sigma squared. So that's the function. Each point is independent, identically distributed, so we can write the likelihood function with respect to all of our observed points of each individual probability density. Remember the 2 and the 6 above, we just multiplied their 2 probabilities and said that was the joint probability. Now I'll do it for all the observations. And so we use this cool capital pi symbol to represent multiplication of a series of things. And we're going to call this whole function the likelihood function of cap x, and it is the products of the probabilities of y given x for every element in cap x. And you notice this has a y and an x, and it has a theta 1 and theta 0. So the only thing that changes in each of those multiplications is the value of lowercase y and lowercase x. So we have this likelihood function. Now we want to find the parameters that make it as big as so working the stuff that's multiplying is a pain in the butt. So we'll just take the logs of both sides. What does logarithmic transformation do to multiplication? It turns it into plusification, into addition. So the log likelihood is the log of this constant plus the sum of the log of all these critters. And then we do that arithmetic stuff that we learned back in the arithmetic class. And eventually we're down here that the log likelihood is minus the log of that constant minus 1 over 2 sigma squared, that sum. And if we clean it up just a bit, the output of the whole thing is a single value is y hat, which is our estimated response, is theta 1x, theta 0. So it's like, gee, that's an awful lot of work to get to the equation that we started with. Indeed, I agree with that. But if we write our log likelihood function using this term, it looks like this equation here that the cursor is moving back and forth on. And to remove the negative signs, we can recall that if we want to maximize a number that's non-negative, that's equivalent to minimizing the negative of that number. So instead we will minimize the negative log likelihood. So we want to minimize this right-hand side. And what things do we get to change in order to make that as small as possible? We get to pick theta 0 and theta 1, or beta and alpha, if you will, because I've changed letters of the alphabet along the way just to confuse you. If we do that, we find out, after removing the constants that don't matter, is we're trying to minimize that thing. Turns out that that happens to be the sum of squared errors, just like it was before if we did good old calculus. And so Bill Nye, it blew his mind. And it'll play that GIF over and over again until you get it out of your face. Now if we solve for the parameters, the sum of squared errors is this thing, which can be expanded as that, which is expanded as that. And then we have already seen that theta 0 is equal to the mean of the observation, the response is y, minus theta 1 times the mean of the predictors x. And theta 1 is the covariance divided by the variant. The covariance of x and y divided by the variance of x, which is what it was before. So that's where our fitting process came from, at least the one I presented. It was basically something called maximum likelihood estimation. In your statistics class, you'll get to see that again, and I'm sure they can make it even more confusing than I just did. Although that's a pretty high hurdle for them to jump over, because looking at your all faces, I think I succeeded in the confusion factor big time. Anyway, here's a function that we just decided to write because we're into that, because that's what we're talking about. We're going to call it the find line function. So let's go ahead and load it. Okay, I didn't get a pink box of encouragement. And so let's go back to the missile telemetry in the previous lab. Because unlike the Chinese, Indians, and Russians, we don't compete in 10-meter air rifle, but we do compete in global thermonuclear ballistic missile launching. And so we want to be sure that this thing is, going 7 kilometers a second when the engine cuts off. So here is our time and speed data again. So obviously we reuse examples a lot because you've seen them before. And so we'll run the find line model, and it tells us that, see the order of that, slope and intercept. It says the slope is almost 12 and the intercept is minus 16. We know at time 0 that our missile is not at negative 16. So we will ignore that for the time being. We can now predict values either by explicitly putting alpha and beta into our prediction model. And the reason this is done this way is actually pretty clever. One of the cool things about NumPy is if one of the arguments in an expression happens to be a NumPy array, it'll apply that to the entire array for you. So y pred, when it comes out, is going to be an entire NumPy array. We're not going to worry about that. We're just going to let it rip. And there's our straight line that we've done before, at least 100 different ways. Now, up to now, we've assessed how good that red line is by how pretty it looks. Okay, does that look pretty? Kind of sort of pretty, but there's curvature there. So we have a couple of ways to assess the quality, and that generically is called goodness of fit. We can assign numbers to our goodness of fit, and from those numbers make a decision. So we're going to look at 3 of the most common metrics for evaluating predictions on regression-based prediction engines. First is called the mean absolute error, or angry absolute error. That was a pun. The mean absolute error is the average of the absolute differences between predictions and actual values. You can think of it as it's a measure of how wrong we are. It gives an idea of the magnitude of wrongness, but it gives no indication of which direction of wrongness. Are we biased high, low, left, right? In other words, where are our shots falling relative to the target? Mean absolute error gives us no information on that. It just tells us, yeah, you're not on target. It's kind of like grades in a class. Yeah, you're not doing great. What am I doing wrong? Well, I don't know, but you're not doing good enough. So that's a mean absolute error. Perhaps you've already experienced that or will, even in this class or in other classes in the near future. But it's not useless. You can think of it as it's throwing away an important piece of information. Am I too high or am I too low, in addition to not being right? But the formula is trivial. MAE is just the sum of the absolute errors divided by how many there are. It has another flaw in that it is scale dependent. So if the values of things are particularly big, it's not good for comparing apples and oranges. Especially if it's not good for comparing little apples and big apples. But it's a simple enough one to create. So here we are going to script it all by ourselves, no help. And we're just going to take the mean of the absolute errors of our speed minus predictor speed, run it, and it says our mean absolute error is 8.9. So when we go back to our red line through our blue dots, the mean absolute error is 8.9. So does that still tell us if it's pretty or not pretty? Hard to tell. We know we have a lot of error here in the middle part, and here at the end part. We're practically dead on right here and right here. So at 2 seconds and 8 seconds, this is an awesome predictor model. This is 2 seconds and 8 seconds is the times you want to use if your kidney is at risk. So a second one is the mean squared error, or the root mean squared error. They're related to one another. And in this case, we square the errors or square the residuals and then compute their mean. Now, this has the advantage of it still doesn't tell us high or low, but it is somewhat scale independent, meaning that it allows you to compare a series of small apples and big apples, small oranges, and tangerines, and ginormous Florida oranges. So the mean square error is take the errors, square them, compute their arithmetic mean. If the mean square error is 0, we get an awesome prediction. As the mean square error gets bigger, it gets less awesome. And it's probably the most widely used measure for regression tasks. The square root of it gives us the advantage of converting it back into original scale. If you look at the formula, we see that these distances are squared. The square root of them puts them back in the same scale, if you will, as the observations. So these are easy enough to compute. In the case of our missile, our root mean square error is 10. The mean square error is 108. So there we go. The arithmetic is quite trivial. And we go back, does knowing that the root mean squared error is 10 help us evaluate that picture? I'd say probably not. And there is another metric in common use called the coefficient of determination. You see it when you use statistical packages and it returns an R-squared. And you will encounter people, well, but R-squared is 0.9, so this is an awesome model. You can, with some creativity, you can get R-squared, it's almost 1, by passing straight lines through circles. So in and of itself, without the graph, an R-squared is kind of meaningless. But it provides an indication of goodness of fit of a set of predictions to the actual values. R-squareds have values between 0 and 1, where 0 is really piss poor fit, and 1 is perfect fit. If you ever do an R-squared calculation, you get 1 back, odds are you've made a mistake. You've calculated R-squared on a variable versus itself, so that should be perfect correlation. So don't ever trust a 1. If that happens, plot it, and be sure that you didn't just plot x versus x, which does happen. I've done that myself. That's why I couldn't keep a real job. No, making that up. It provides a measure of how well observed outcomes are replicated by the model based on the proportion of total variation outcomes explained by the model. 2 periods. Here's the formula. So we compute the total sum of squares, and then we compute the sum of squares residuals, which is the observation minus the fitted model. What's left is called the residual, and we square that thing and sum it up. And then R-squared is 1 minus the ratio of sum of squared residuals minus the total sum of squared. Easy enough to code into our friend Python. And in the case of our missile, our R-squared is 0.92, which is a pretty good value for R-squared, although we still know that that is not the best model we could have picked. The best model we could have picked would have had a time squared term in it, because I invented these data and I happen to know it's quadratic. But you wouldn't know that ahead of time. So for linear models, that is a pretty good R-squared, and at least over this particular range, it's a useful predictor. If I was to ask you what is the speed of the missile at 7.5 seconds, assuming you can actually see the numbers up there, you would conclude that it is 60 something. Good. All right, so here's the part that was just grabbed from something else, and I haven't had time to tidy it up. So we've done all that. So here's the picture that we're working on. Our black line is the prediction. Our blue circle is the observation, and the red arrow represents the error. And the thing we're trying to do is avoid this particular picture. So we built this model, we made a prediction, you trusted me, and I failed. We want to minimize the number of times that this guy has to do that line. He died recently. I think the actor is no longer with us. He's now a gardener pushing up daisies. A related question is, how confident are we of our prediction? So in addition to producing our line, we can also produce interval estimates of predicted values and interval estimates of the alpha and beta. I'm going to skip the arrows and Horace and Daryl because we have just addressed this. So this one they were using arrows. I much preferred the Olympics. And so let's go ahead and try to refresh these ideas of bias and so forth. And for me to run this simulation, I need to find advertising. Is that the right one? No. That is not the right one. Okay, so who remembers how to go ahead and get a file automatically? I'm going to go with that'll be a nobody. Let's show you the cool thing about having all your stuff. I think we did that back in lesson 19. So we're going to perform the miracle of hopefully we have the miracle of cut and paste. I think I'm being a dumbass. Why don't I just use the editor? Let's say import request. There are no requests there, so that would not be a good idea. $18? Yeah, 18 probably has a request in it. File. There. So we'll go to our lesson and we're going to go ahead and hit paste. It's in databases and the name of it's advertising. And I'd be paying attention to this, guys. This is not time to be sleeping or checking your phone. Unless there's a good price on magenta scrunchies. Okay, so rather than go out to the internet and look up how to do that again, what did I do? I know I had it working for something before, so I just did it again. So let me go back to my lesson 20, and there's two things that can happen when I run this script. What I want to have happen, which is for it to work, or, God forbid, it just breaks. Now the extra bonus feature making this a challenge is look at that URL. Okay, so that's the class server that we've been using. But look at where I'm operating. I'm on a different machine. So I'm pretty sure that database is already on the source machine, but we'll find out real quickly. That's a bad word. We will try that again. Let me see. Delete that one. Let's go check databases. Oh. Occasionally, I guess you got to get the spelling right. That means that's going to need to be a capital A. All right, in a matter of minutes, we've done stuff that weeks ago would have taken days, or I did what you did and it didn't work. So now let's hope it worked. Hold on. Bingo. Okay, so that is uber cool, I think. You may not think so, and that's fine. You only have to think it's uber cool for about another week, another month. This is November, yeah. Oh, but we lose a whole week because of thank heavens, the bestest week in all of November. Although we have a class on Tuesday of that week. That stinks. I really want to do that online so that I could not be here. And I know that the 11 of you aren't going to complain, but you know, there's those 41 people out there in invisible land that are going to miss this. So we might think of another game to play on. Yes, and I know this is being recorded. But given that Catherine's the only one that watches the recordings after the fact. So how far can you get through them before they put you asleep?
Probably halfway.
Oh, I'm impressed. Yeah, I'm impressed. You do know you can fast forward to the stuff that you're looking for.
That's typically what I do at the halfway mark.
Oh, good for you. Yeah, that is how. Or you said that the Pascal was that. It's like, oh, good God, man! Just use the right thing and stay off my case. But you can't type that back because I would not want to have to use the engineering media site to store all the videos. If you think YouTube's bad, you got to imagine what we do here. It's awful bad. Okay, we have imported our file named capitaladvertising.csv, and we're going to load it in. We're going to get television, radio, and newspaper, and sales, and then we will make our prediction model with TV, radio spending, and so forth. And so let's go ahead and just run that. I don't think there's any plotting going on. And I think it ran. I'm going to run it again. It always scares me when it runs this fast because we're connected to a Raspberry Pi computer that is duct taped to my television set at my house right now. So having it respond that fast scares me because that's a $40 computer with like about a $35 little SD card in it that is outperforming the building full of machinery over there at TPLDC KQ's WA6DRP. So now let's compute our root mean squared error for television spending and radio. Who recalls from your memory, we're not going to go back and look at it, which one was the most productive spending of money in terms of making sales? Radio. I think you're right. I think it was radio. If we look at that, it says the root mean squared error for TV is 3. The root mean squared error for radio is 4. So from those two, those are not, without actually plotting it, we don't really know. But those are reasonably low numbers. It's telling us that those two models are pretty good linear predictors based on the data we have to work with. If we do the R-squareds for the same thing, we get a slightly different story. R-squared for TV is 0.61, which is above half. It's not great, but it's usable. R-squared for radio is 0.3. That's a little on the low side. I wouldn't bet your life on it, or mine. So let's look at our Pearson correlation coefficients for both of them. And it's just numbers. The sales are pretty well positively correlated with ad spending. 0.78. What's the biggest a Pearson's R can get? 1. What's the littlest it can get? -1. For radio, we're at 0.5, which is weaker correlation, but usable. And we'll use another external thing that gives us evaluator results, and we're going to look at the somebody's, can't remember the name. It's like Nashville it's a measure of, oh, I couldn't find it. We will skip that for the time being. Hopefully we don't, oh, I guess we can't skip it. So what happens when you import something and it doesn't work? Remember what you have to do? On your computers, you can probably do this directly in Anaconda. I'll wait for time good. What is my password? No, I'm not that dumb yet anymore. I've got it. Okay, so now I'm root and I need to get the okay. Actually, I think they just go straight to pip. Well, what's the worst that can happen? You can sit there. Didn't like that, did it? On your computers, you probably don't need to use the sudo. You use the Anaconda PowerShell prompt, which gives you a terminal interface like that, and then you type the path to wherever you installed it on your machine. Okay, so now we will go back and hopefully we will have addressed the pink box of encouragement. It's not going to work for me today. That sucks because this next part does pretty cool stuff. Our goal is to be able to get pictures like this. So I'm just going to skip ahead. This black line is our prediction based on a maximum likelihood estimate. The maximum likelihood estimate, or minimizing sum of squares, produces a single result, which produces that black line, where these dots represent our observations. And we can produce interval estimates on the slope. That's what these curve-like looking things look like. And what that's saying is that the probability that the slope is 95% of the time is somewhere in these ranges will be between those two lines. That's an interval estimate on a parameter. Another type of interval estimate is on the actual predictions, and they tend to be wider and a little bit straighter. And so here's our observed value, here's our model, and we're interested in the lower and upper prediction limit. And these have the same analogy as a 95% confidence interval or a 5% uncertainty interval is that we've done before. And they're almost constructed the same way. I'm going to scroll forward and see if it does the pictures. I do not have it plotting the pictures, so I will get that for our next class meeting. I'll have this all fixed and running correctly. Just for fun, let's see if this even works at all. Okay, that ran. And here it's giving us the value of the constant, the value of the slope, in this case constant in x1, the actual coefficient, the standard error associated with it, and its lower and upper prediction interval. So in this particular example, it says that the intercept is minus 16, but it can be as low as minus 31 or as big as minus 2 and still have a probability of being correct of 95%. The slope is 11.9, but it can be as low as 9 and as big as 14 and still have a 95% probability of being correct, if you will. It gives us the p-value based on a t-statistic at rejection. And when I get it working right, I can get it to plot the two curves. So there is the lower prediction intervals, the upper ones, and I guess we could plot the whole thing. Oh, it looks like I attempted to it. Without debugging it, let's just see if this all works. Sweet. Okay. That actually worked. So, brief wake up from your naps. Good. So here we have the whole deal, everything plotted here. The blue dots are what? The observation. There's 11 of you here, so I should be able to ask these questions and get an answer. The red line is the prediction model. Good. I'll help with the other two. I guess that's orange. The dashed orange lines that are kind of wide at the left end and wide at the right end, and they pinch in towards the middle. Those are the 95%, I think it said 95% confidence intervals on the slope and intercept part. So those are representing where that red line should fall with 95% confidence. You'll notice that the red line will always pass through the mean of the x and the mean of the y. It does that by design. So you can think of that line as tilting and maybe sliding up and down. That's what those orange ones are. The green ones are the 95% prediction intervals. So for example, let's look down there at an x value of 2. So an x value of 2, our predicted speed, at least from the plot, is a little bit bigger than 0. We could go look at the table and see what it is. But it says with 95% confidence, it could be as low as minus 25 at 2 seconds, or it could be as high as plus 40 at 2 seconds. So that's what the green lines are representing, a prediction interval. In the case of a ballistic missile, negative speeds don't make any sense. I guess they do if you're like launching from a submarine. You get negative speeds. You need to dive and ram that submarine as fast as it can go and get out of the way because it's coming back to get you. I saw Hunt for the Red October. They did it. That was a cool scene in the movie. If you haven't seen the movie, it's not that big a deal. But I like the restraint the crew says after the captain just killed them with their own torpedo, because they knew it was going to hit them a few seconds before. I'm surprised they didn't pummel the crap out of them. Okay, that was what we wanted to accomplish today. I apologize for the rather rushed part of the latter part. I'll get this tidied up a little bit. Fortunately, that all worked. What threw me off was this broken part here, because these Nash-Sutcliffe error evaluators are really useful tools in helping understand the uncertainty. But the end goal of today is you've at least seen how to get a prediction model, and you have tools for that already. You know now what philosophically is meant by an interval estimate of the parameters. You get the interval estimate of the parameters, at least in this example, from the ordinary least squared regression table. That's what this part of the table is showing you. These are the parameter interval estimates. Then we made the prediction estimates by using some tools that are also built into the least squared things, and we can get those intervals separately. So there's two different kinds of intervals. These are really important. The ones that you'll see in your statistics class, which will be the orange. I wonder how professional actors do it, which will be the orange ones up there. You'll see those a lot. Those are visually conveying the effect of the parameters, the slope and the intercept. And if you have more predictor variables, the various values of those. But a more practically used to engineering application are the green lines. That's what matters, because if it turns out that you're inside the green line, you get to keep your kidney, well then bueno, right? But if falling outside the green line is bye-bye kidney, you would very much like the green lines to be wide, or to be sure that it's somebody else's kidney that's at risk. So the prediction estimates are far greater importance than the parameter estimates, although they don't get as much coverage, except they do here. So for instance, if at 5 seconds, if our missile was going 100 meters per second, that's outside the prediction interval. That's pretty, based on those green lines, that's pretty unlikely to happen. Our green lines tell us that the probability of that happening is, you actually can answer that statement. The probability of getting 100 meters per second speed at 5 seconds is not 0, less than, no, 95% in the green line, so 5%. Yeah, 1 in 20 chance of that happening. So when that comes back, you go, well, there's something wrong with the telemetry. We need to spend another $2 trillion to make sure that the wireless connection is working. That was not meant to be cynical. It's when I was a kid, there was this place called the Soviet Union, which was our mortal enemy, and we were going to cease to exist because of them. It didn't quite happen that way, but there was a thing called the Sprint missiles, the fastest object human beings have ever built. It accelerated at 10 Gs for 75 seconds. So pretty much the same kind of thing that we have here with our fake ballistic missile stuff. It went so fast that it created a plasma around its nose cone. And so it was radar guided. It couldn't communicate with ground control station. They shot a bunch of them during testing, and they just wandered out and did what missiles do, just like they do in the movies. So the response, because at the time, Raspberry Pi computers hadn't been invented yet, so you couldn't put good computers in the thing and just tell them where the missile started life at and run accelerometers and let it keep track. So they went back and spent $2 million making a 10 megawatt maser. It's the microwave amplification by stimulated emission of radiation. So they made a 10 million watt microwave communication thing to talk to the missile. And that worked. That did what they had to do. Fortunately, they never had to use them on anything, because they shot them at towed targets, and occasionally they'd hit them, but most of the time they'd miss. Something that's accelerating at 10 Gs for 75 seconds is going, I think, 14 times the speed of sound by the time the engine burns out. The fastest object we've ever made. I guess a laser beam is the fastest thing we've ever made. So in that case, if it was going outside the green thing, they would just go ahead and go back to Congress for more money to fix the radio. And that'll happen in your careers. And hopefully, it'll happen favorably for you. All right, well, that was kind of a rambling thing. We will get on to